you. Yeah. Okay, thanks, Stan, for inviting me here to give a talk. I was here like 4 or 5 years ago, certainly before pandemic, and I really like my Southern California visit, so I decided to move here. Okay, so great to see everyone. My great pleasure to present recent work on trustworthy AI. It's a very vague word, but I'm trying to make it more precise. Okay, so let's start. I think AI 2.0, in my personal opinion, is that we are no longer pursue the performance, the accuracy, right? See, I'm trying to make the minimum mean square error, right? So we probably need a big thing beyond that. Is the trustworthiness is something. I think that's the major drive for the second generation of AI. Okay, because now the model architecture become convergent. So widely applied. So we try to think about the privacy, fairness, and robustness. That's what I call as trustworthy. Okay. Yeah, just let me give you a few examples here. I'm sure you read all this news in the newspaper. So in recent data leakage incident, like Google actually exposed the private data of the people. Among about like 500,000 former Google Plus users to outside developers. Okay, and also an AI algorithm like supporting the resume screening for employment at a large tech company was found to be biased against the women. Okay, and actually self-driving car actually the accident often happen in the so-called corner cases. And that make people not trust the machine learning algorithm, especially CV algorithm, so much. Okay, and also social media always like push you the news that you believe you like, and somehow it's called like information component. And from my students' own experiences, they will have this so-called like a video interview. You record a video of yourself, you email or you send, upload it to the Thai company, and they will use the machine to decide you pass the interview, the very initial screen or not. And from my students' experience is that if you speak a non-native speaker, you will be very easily fail. Okay, but we know the accent shouldn't be a qualification they evaluate. Okay, so the first topic is privacy, and the paper is called the online forgetting process. We consider super simple problems in every problems I talk about. And what's the forgetting process? We have the right to be forgotten. Say, for example, I'm a client now from bank, but I left at the bank. I will no longer use it use it for a year, but next year I left. Then they should delete all my data. Okay, either there's such a rule within like 3 or 6 months, and they should delete the data. But at the same time, the bank itself still want to keep the information. How they do that? Okay, what's the best way? That's our own right to be forgotten. Our data should be forgotten. And here is a very simple mathematical framework to say, okay, let's just consider linear regression. I have all this like up to S data. And in the next day, I have a new data coming in. Okay, this can be a new client or can be anything new, but for many reasons, regulation or maybe hardware constraint, I have to delete the oldest data. Okay, so in other words, I update my linear regression or even the deep neural network because I have a new data. I throw away the oldest data. Okay, for regulation reason, for example, and we would like to see all this updated or retrained estimate how that will change and what's the best way to estimate the linear regression. And our optimization matrix is a regret. Okay. Okay, here's the linear regression setup. We have y and we have x. Theta is unknown, something we want to estimate. And we use this called FIFD, means the first in and the first delete. Okay, so we delete the oldest data while receiving the newest one. Okay, certainly you can delete more than one data. Here, just keep everything simple. One data come, you delete the oldest one. And the ordinary least square estimator is written as the OLS form, just like this one. Okay, and this is phi is the gray matrix. Okay, it's very simple. And this is the T as you t grow, then you have a updated estimator. Okay, then what
the S is the after S kind of rounds of forgetting, right?
Yes, the S is the length of the data, the sample size is a fixed. Yeah, you have one more data, you delete one more, but this S is a fixed.
S is this number, how much I do this like step deletion, right? One step.
Yeah, the sample size, you can think how many data are you.
Because there's also data that are left, right? That are left in the sample that I did not delete, right? Because there was also this T. S and T.
Yeah, T should be larger than S, certainly. I should accumulate.
T is the whole horizon.
The whole horizon. Yeah, S is a fixed number. Okay. Yeah, good point. Yeah. So one thing we need to take care about is the behavior of the grand matrix, because that means as time goes, I delete one row and one column. At the same time, I add another row and another column. So this grand matrix always remains the same size, but just maybe one row and one column got replaced. Okay, so it's not surprising. It's a very simple linear algebra problem. You can tell that you will have some rank perturbation, right? Okay, you will change at most rank 1, or you don't change, right? Okay, if you are lucky, because you only replace one row and one column. And here's a finite sample result: is that the perturbation is larger than 1, but in theory it's 1. Okay, so that caused some trouble. Even we do linear regression, because the rank of the grand matrix is not stable, right? One way to do so is that we stabilize the grand matrix by plus an identity matrix. That's a simple trick. This is also the form for the so-called Regression estimator. And all the technical difficulty is how much stability you want to add it. In other words, how you choose the lambda here. This lambda, of course, should change as a time t. So I use a lambda subscript t minus 1. Okay, so actually our contribution here, I didn't talk about any technical details. We use some online learning results, some random matrix result. If we set this lambda as an adaptive way in this form, sigma is the error variance, x is just a feature vector, take a supreme norm, and s is you can think of the sample size, d is the data dimension, and divided by the uniform norm of the seed star. Okay, this actually gives you the minimum regret. Okay, and here is the online update the algorithm, because that's an OLS. We have explicit form. We don't need to retrain for each day. Okay, we can just do the update, online update. Okay, this it's a moving window trick if you know time series. Okay, so we can consider both the case that the dimension is very high, larger than S, or dimension is smaller than the S. You can do the S as a simple size. Okay, this applies because we are doing this regression. And here, this is the result I want to show you. One is that you take the adaptive lambda, which the theoretical, inspire the choice. Another is the fixed lambda. Without theory, you can only choose whatever the best, in the beginning, then you keep using the same lambda. Okay, for example, 0.01. But actually, in our theory, we show you have to do an adaptive way. So basically, here y-axis is just a regret. Here is the time horizon t. And the point I want to make is if you use the adaptive regularization, see the blue line, then you always have the much lower regret comparing to other ridge regression with the fixed regularization. Okay, and we can actually, the result is very robust in the sense of we can change the value of S, the sample size, and we can also change the noise level, the sigma. So we got like a persistent result. We repeat like 100 times. Okay, and we can also do one more example experiment. We add more. We add like 2 data, then we remove 1 data. Okay, that means as time goes, the S becomes larger and larger. Accumulate more data. Then you find the same result. And in particular, because S grows, then you can find the less often we delete the data. Like we collect the 2 data, we delete 1. This is the more often. This is the less often we delete the data, the better the algorithm. That makes sense because your S growing, right? You collect more and more information. Certainly your regret will be smaller. Okay, there's nothing surprise. Okay, that's the first thing. That's how people and actually some industry, especially financial industry, how they use to protect the privacy. Okay, they just delete all the data. At the same time, they want to maintain the information. Yes.
And just a quick question. Can you briefly comment on what type of adaptive selection procedure for lambda are you using?
Oh, here is the mathematical formula. Actually, it's the exact formula, so it's no approximation. Of course, the C star we need to estimate it. We can use some initial, estimator for that. Let's get some consistent estimate.
So it's not cross-validation.
We don't need to use cross-validation.
If something is random, you can run in parallel, right? You can run lambdas on lambda still depends. The best depends on theta star, but you can run like a few copies of the algorithm.
Yeah. You can have some like. Yes, you can. In the beginning, you don't need to use a pattern estimator. Okay, good point. I didn't talk about too much practical thing, but it's a yeah.
Sorry, question. So you said it's better than the fixed, better than the
fixed lambda.
So you mean better than the lambda fixed in time?
Yes, fixed in time. Yeah, we just fix lambda like 0.01 as all the time. Because if you don't have a theorem,
better than the best lambda fixed in time, but no in time.
Because here we use a regret. Regret means that you choose the best lambda compared with that.
I know, but yeah. I mean the regret. It's an actual regret scenario. You do have some regret on which you prove our performance, right?
Yeah, we have like optimal result. This regret, what device a regret, and how are we going to achieve that?
And we will get to that. So
no, we don't, because here we had all the theoretical results in this single.
Maybe I should ask the question later on.
Okay, yeah. I didn't prove that. What? Okay, just assuming that you can have an oracle that can choose the best lambda so that the loss is the minimum. Yeah, there's a way to define the loss. Yeah, which I actually put in the appendix. Yeah. So sorry, I didn't talk about too much math here. I just tell you how we protect the privacy. Yeah. Okay, the second talk is robustness. And robustness is something really big. Imagine you have Tesla, many of you may have that. So what if it rains, right? What if it's foggy in the morning, right? You still want your car to, recognize the road and a lot of things, right? So this is a very famous example. If you add a very little noise, I mean, by human eyes, you can still tell that's a stop, right? Stop sign. But if you use a machine, they will tell that's a max speed 100. Okay, that's what really happened. There are many such CV computer vision examples. That's so-called adversarial perturbation. Okay, so what happened? That's one way to expand it. So the noise will attract this positive example to cross the decision boundary. That's how the noise has been adversarially designed. It's not a random noise. It's a noise that to make that you make the largest mistake. Okay, in that case, certainly you don't need a random noise. You just need to move the example nearby the decision boundary to cross the decision boundary, right? Then you make a mistake. So people too, if you want to get a robust machine learning result, they have so-called adversarial training. Basically, it means that I just train your training example in the way that you make the largest mistake. You use that like a kind of pseudo examples to train your machine learning. I will give you that min-max formulation in the later pages. Okay, but basic idea is that I just want to train your machine learning algorithm in the worst possible scenario. Then when you see a very bad scenario, you can still make a right decision. Okay. Actually, there are a lot of like data competition for adversarial training. This is something like I think at least half a year ago, we got this table from this robust benchmark data from in the GitHub. Actually, if you know, they have the SOTA, the state-of-art adversarial robustness for a standard CIFAR-10 data set. Even they apply the state-of-art adversarial robustness, so the accuracy is still very low, 66%. Okay, so even they apply the best at that time, the best like adversarial training, the accuracy is still not so good. Okay,
and that's accuracy for driving.
For accuracy, so the classification accuracy will be downgraded if you apply the adversarial training. If you
okay, for this specific data set.
Yeah, for this specific, 50%. Yes.
What is the?
It's just how you measure the perturbation on the data.
And what it means that
it means that so you actually distort your example in within some distance. How you measure distance? I use L infinity as as a way to measure the distance between two vectors. One vector is a real sample, and the other vector is adversarial sample. The distance is measured in L infinity. No, yeah, it's just a standard way to do that. Okay, so why that happened? That's what we care about. Okay, why do adversarial training? You got the more robust result, but your accuracy reduced so much, right? So I mean, here is really depends on how much the adversarial noise you consider. If the adversarial noise is very small, then that's the case that the clean training and the adversarial training will converge to the same C0. If adversarial noise is like a medium attack, you see a medium level, then actually this adversarial training will convert to something different from C0, the ground truth. And if even you get a very big adversarial attack, okay, basically that's a random walk. You can imagine if and the noise is much bigger than the signal, basically you cannot do anything, right? That's not a regime we care about, okay? And actually, in the simple linear regression, we verify, okay, we have a conjecture and we prove that if the adversarial level of attack is larger than root of D over N, this data dimension, N is sample size, then actually you will deviate from the clean training trajectory to this trajectory. Okay, that's a phase transition. So you can imagine if the ring is so big, then even your eye couldn't tell that's a false line. There is a phase transition. We figure out what the threshold is. It's a root of D over N. And then what's the solution, right? So that's just the phenomenon. You can explain in theory. But what's the solution for that? A simple solution is that we have more data, right? Then that will help. But data is very expensive, right? You collect, especially the label data, right? You have to send your car on the road, and if some car accident happens, you collect a very important data point, but that's too expensive. You cannot afford that. Then there are some like unsupervised learning. So you don't need the label. One is called self-supervised learning, and another one is called synthetic data. I generate some like data. I don't collect the data from real world. I generate it in some way, which I will describe. That's something I'm going to talk about. This is really like a magic to me, because when I first saw a paper by DeMind, they actually get something from nothing. Because sample size is always fixed. Using this fixed sample size, you generate a artificial data. Okay, then supposedly that will not bring you anything more, right? Because everything just in the raw data. But if you look at this computer vision example, you will notice actually they can bring in the so-called robustness. Okay, here's how they do. Here is S1 is a real data set. And they actually can use a real data set to generate X, the feature, the picture, okay, all these pictures. At the same time, they can use the same real data to train a clean classifier. Then they can feed all these features into the clean classifier to say, okay, this picture is a cat, this picture is a dog, okay? In other words, the generated data, has a estimated or predicted, the label, okay? Remember, all this like a label and the picture were generated from real data. And here we can get an unlimited number of data sets, right? That's called synthetic data. Here the question is, what if I mix the real data and synthetic data, use that to train our machine learning algorithm? What's going to happen, right? Traditionally, people just have one real data set to train the machine learning. Now I use this real data set to generate another data. So I mix the both. I use that to train the machine learning. What's going to happen? Actually, they prove, not empirically prove, not like mathematically prove in that paper, is that here is the proportion of real data. So if it's 100%, means you don't mix the synthetic data with the real data. So we look at here, you notice that, for example, in this point, 90%, if 90% of the data you use to train is from the real data and 10% from the synthetic data, actually you can get a better, like a robust test accuracy. Okay, that's some accuracy and like a robustness scenario. Okay, so you indeed gain a robustness. That's really surprising to us. Why? Because since you get a robustness without paying anything, right? You still use the same amount of data. You just use the data to generate a new data. Okay. So we have curiosity in theory. So why this artificially generated data can boost adversarial robustness? And this seems like a free lunch, right? Okay, so before we do any math, we have some high-level intuition. The first one is a stronger attack perspective. So using generated data, I mean, can be viewed as adding a corruption into the original data, right? Because imagine you are estimating the underlying density, for example, and your estimation certainly not correct. I mean, it's not 100% correct for finite sample case. Then you use that estimated density to generate data. So basically, you add the corruption into the original data. Okay, this actually amounts to introducing larger adversarial level epsilon. Okay, I will define what the adversarial level is. And the one adversarial level epsilon is slightly larger than used in robust testing. Actually, the robust testing accuracy will be improved as the interval observation. Okay. The second intuition is that it's from the robust model perspective. We just consider very simple linear regression, and we have a clean regression, and we also have the robust regression. This is from the results from another paper of ours. And actually, as you can tell, in the robust regression, we have a covariance matrix sigma, covariance of X. And if we can have a better sigma estimator, the robust regression will behave better. Okay, that's another reason, yeah, why that's of course very heuristic. And then we come to the mathematical part to make our argument more good.
Okay. So in this formulation, what was this on the previous slide? So this theta epsilon, what is the theta epsilon?
Theta epsilon is that given that you have like your data has this adversarial noise, and the adversarial noise level is described by the epsilon. Okay, given you don't use the raw data, you use the data with some adversarial noise. Okay,
so you corrupt your regression coefficient.
Yeah, I corrupted, yeah, and then I use corrupted data to learn this and name it as theta epsilon.
Okay, so the data, the corrupted data is generated from the theta epsilon.
Yes.
Okay.
And here is more how we train it. There's a review on the adversarial training. Probably I should present this earlier, but here we have a so-called loss functions L0. That's what people usually define. We have another like a so-called adversarial loss. What's that? That is the X will be add some noise. A means a noise, A epsilon. It's not like random noise. It's depending on the X, depending on the Y, okay, also depending on the F, okay? And how we define this adversarial noise? This adversarial noise is the one that can maximize your loss given X. You see, that's how we define, because that's I want to add a noise so that you can make the largest mistake. Okay, that's how we define A epsilon, not a random. It depends on X, Y, and the underlying function. And we added back, and this is the adversarial corrupted X. X plus A is the corrupted X. And then once I have an adversarial loss, then we can define the empirical adversarial loss. I can define the robust estimator that just minimize the R hat. Okay, so it's a very mathematically, it's a very well-defined difference that the noise itself is data dependent, right? Not like what we learn from statistical measurement error, right? In that case, that's a Gaussian noise, but here noise is like a data dependent. Okay, how we estimate, how we do the analysis, we actually do a very careful analysis on the so-called excess adversarial risk, EAR. And this EAR is actually proportional to theta minus theta epsilon. Theta epsilon is the adversarial robust estimator. And actually, yes.
Sorry for interrupting again, but so this is all done under against some kind of infinity constraints on the noise, or?
Yes, it's given a
what's the constraint?
It's a ball.
BP,
right?
Okay.
BP is like a LP ball.
LP ball.
Okay. We also have L infinity result. We present LP ball here.
Okay, so you don't allow the basic noise of arbitrary magnitude. It has to be bounded.
Yeah, really, this is a metric sensitive result. In other metric, you can have different results. It's a good point, good catch. I didn't talk about how we define this distance. Okay, that's LP. And actually, the way we analyze it is to measure this x-axis as risk, but we use adversarial, right? Because that's the adversarial, like a cleaning, right? And actually, we do a decomposition on this one. Okay, basically, we can decompose this risk into two parts. One is the label cost, and another is the generator. Remember how I generate the first? I generate a picture. Okay, that could be not so similar as a real picture, so you pay a price for that. At the same time, you give a label of that picture, okay, and that may not be accurate enough, so you pay a generator cost. Basically, what we did is do a very careful analysis on the label cost and the generator cost, and here is the E1 represent the labeling cost, and E2 means the generator cost. Actually, we can do a very careful analysis. So for ideal generator, that means the picture you generate is exactly the same as the raw data. Okay, in that case, the expectation of your generator cost is 0. Okay, in average, so you don't pay any cost. That's the case that certainly you have a smaller adversarial risk. So that's the case. That's for clean training. If you have an ideal generator, then actually you have a much smaller, risk in terms of robustness than the one that you do not use the synthetic data. Okay, and however, sometimes your generator is not so good. That, of course, that should be the true case. In reality, your generated image has something not so similar as the real data. Then you pay a cost. But if your generator, for example, some diffusion model is still good enough, so your generator cost is still not big, then you can still beat the one that you only use a clean data as a training sample. Okay, and if I have a poor generator, okay, you generate some picture which doesn't look like a cat or doesn't look like the dog, right? Then of course you mess up everything. Okay. So our contribution is to mathematically to analyze the E1 term and E2 terms. And here we actually can use the theory to explain the empirical finding in Guang's paper. And for low quality generator, we can prove the mean of the generator is even not 0. Okay. Sometimes it goes to 0 for good generator, or for bad generator, it doesn't go to 0. Then of course you have very bad robustness. Okay. Okay, I think I'm pretty much finished the second topic. Yes.
Is way more, but like, does this give sort of any sense of how much data you would generate ideally? I mean, if you have like a perfect generator, you just generate as much data as you possibly could. If you have a terrible generator, you can generate very little at a time. Is there any intuition for like where it goes?
Oh yeah, that's a very good question. I don't think our theory can give you any practical guideline. So what kind of generator you should, just like intuition. I mean, to be honest, even you don't do that, you probably can predict that you should do a good generation, then you will increase the robustness. My theory is more like a conform what people's intuitions, right? But we cannot predict how we get a good generator. Unfortunately, that's because our result is too general. If we specialize some very simple, very specialized generation, we probably can answer a question. Yeah, a good question. Okay, another one is fairness. This theory is a useful theory in the sense it can help you to develop an algorithm rather than to explain why algorithm works. Okay, so we know we have this fairness to very frequently. Okay, so here is a review on the fair algorithm. So here I just give you some high-level ideas, then I give you definition what I meant by fairness. Okay, so existing fair algorithm can be classified into 3 classes. One is called the pre-processing. That means, I believe all the bias is rooted in the data, right? If the data has so many male, very little female, this imbalanced data will actually deliver some like unfair decision. I just rebalance them or up some or down some of them. Okay, it's called the pre-processing, and but some literature also show that the bias can still happen even after you remove the bias, because the algorithm itself may introduce new bias, right? So the second approach say, okay, I do an in process. And what I'm doing is very mathematical. I just do a constraint optimization. I do optimization for performance, but given a constraint, like the fairness is smaller than something. Okay, but the problem is that the fairness constraint is usually non-convex. So your optimization, may not convert to the optimal global optimum. Okay. The third approach is called the post-processing. That means I don't need to do anything about the data. I also do not change my algorithm. I just change the threshold and you compare while you make the classification. Okay, that way is the one I'm going to talk about. But how you change the threshold in the classification is non-trivial, right? Say maybe I give a high bar for male, lower bar for a female, one do classification, but how you adjust up, how you adjust down, away from the half. Okay, that's not so clear. Okay. I will show you like a difference between two conditional probability. Okay, so there's some precise definition. Okay, so what we have our contribution are twofold. The first one is that we prove, okay, what's the biased fair algorithm? That's called fair Bayes optimal classifier. So basically, we want to answer the question that what's the highest possible classification accuracy and the fairness constraint. That's a pure theoretical question. I'm not talking about any algorithm. I just say, okay, in theory, what's the best you can do, given the some fairness constraint, which I will define. And there are some earlier work. I probably don't have time to go through them. The second contribution is about the mathematically. Okay, now I know what's the best you can do. So can I develop some algorithm to achieve that benchmark? Okay. So we have some called the theory inspired fair algorithm. Actually, you can find other sort of fair algorithm, but they usually do not have a theory inspiration. It's more like some of them are like a more engineering type of work. I will explain how the theory will inspire the fair algorithm. First of all, our results can apply to lots of group fairness scenarios. So fairness has many definitions. A big classification called individual fairness and group fairness. In this talk, I only care about group fairness. Even for group fairness, you have many ways to define. Okay. And actually, for this algorithm, it has a direct control on the level of disparity, and we can also consider both the exact and approximate fairness. Exact is also called as strict fairness. That's something too much. You have to reduce the accuracy law if you want to maintain a strict fairness. Okay. And specifically, we algorithm-wise, we just developed a two-stage fairness algorithm. First one, I think there are two features of this algorithm. One is that the level of disparity is that directly specified as an input parameter, that it has a high transparency. If you read other fair algorithms, this implicitly determine the level of disparity. And it is also computationally very efficient. Okay, let me give you some formulation. Okay, we just consider a binary classification problem y01. I give you a loan, or I approve your loan application, or I disapprove your loan application. Okay, and that's the y-axis, the applicant, the features, where this guy lives, gender, education, year, okay, and also the race and many things. Some of the features are very sensitive, right? So I say the sensitive feature, I call it as A, or called the protected features. A is for simplicity, we just consider A is either 0 or 1. You can see the white versus non-white, male versus female, right? And for unprotected features, for example, say the education, for example, that's not too sensitive. Maybe I put that as an unprotected feature. And for credit lending setting, Y corresponds to the status of repayment or defaulting to a loan. X is a common feature, such as like education of income. They certainly matter to the Y, right? But they are not sensitive. But A indicates like gender or race. So how we define the fairness? Okay, fairness. What I meant by fair, that's just one definition of fairness. There you can find other definitions. Given A is 1, say A means gender, the probability that you get your loan application got approved should equal to the probability that you are failing. This is zero. These two condition probability should be equal. That's called fair. Okay, and it's called statistical parity. And what's the level of unfairness? I just measure the difference between two conditional probabilities. Like a male get like 90% of approval rate, female get like 10%. That means 90% minus 10%. That's too much, right? So we want to minimize that. Okay, but sometimes that will cause the lower accuracy. Okay, how we control that? Okay, this is so-called demographic parity, and our framework also covers some other definition called equality of opportunity, predictive equality, overall accuracy equality, and the predictive parity. There are lots. Okay, I don't have time to go over all of them, but let me take this as an example. Yes.
Population, there is like
yeah, group means that the two population wise they are similar, not individual wise.
Because I mean, it seems that this criteria doesn't care what is the a priori probability of A0 or A1. This is conditional.
A conditional given that this
a framework works when a priori the probability.
I work for both the equal or the difference more than 0.1, for example. It's called approximate. If they are exactly, if this DTP is 0, that's a strict parity. If it's but our result apply to the approximate and the strict. Okay, basically that's the one. Maybe answer question. There's a difference in conditional probabilities more than delta. Delta may be something that the government decides. Okay, this should be at most of 40%. There's a 60% difference. Cannot be the difference cannot be go beyond the 20%. Okay. Now, given the delta, okay, so what's the highest probability that you make a mistake? Y not equal to Y high, that's the misclassification rate, right? Actually, we can prove if you D star is that, okay, what means D star smaller than delta? That means if I do not consider the fairness function, the differences is already, I mean, smaller than your delta. Okay, even I don't impose the fairness function, I compare to conditional probability is just like 1%. It's already smaller than the 20%. Then actually you just use it, right? That means the constraint, the fair algorithm is just the unfair constraint. Okay, that's the uninteresting case, right? The interesting case is that if I don't impose fairness function, the difference is like 30%. But by law or whatever rule, that shouldn't be go beyond 20%. Then how should you modify your algorithm? Here's how you modify. Basically, what you have done here is to change your thresholding. Okay, if there's no fairness constraint, then you just compare the conditional probability with half, right? That's a population case, right? But here, okay, depending on the A, if A is a positive 1, that means half plus something. If A is 0, that means half minus. Our contribution is to figure out what's the biased way to adjust up and the biased way to adjust down. And that is also depending on the PA. That what's PA is the probability of the male and the probability also matter. Okay, how you adjust depending on the probability of the gender. T del star is from a equation, very long equation. I didn't put here. Okay, based on delta, yeah, based on delta, and that can be explicitly solved. Just very long, I didn't put here. Okay, so everything can be explicitly solved. That's the whole point. And actually, here is the key figures I can show you. The first row is the differences in demographic parity of the three classifiers. The first classifier is the one that I do not adjust the thresholding. This is the one that without the fairness constraint. And this shaded area is the level of disparity. Okay, you can tell if I do not adjust the level of thresholding, then this is a pretty big area. Okay, however, I can adjust. That's the way I adjust in my thresholding. You see, this red line is larger than half, blue line is smaller than half. Okay, in this way, I can actually shrink your disparity level. Because this shaded area is smaller, I can precisely to draw the picture because I have a explicit mathematical formula, and I can go straight so that there's no more shaded area. That means strict, that means a strict, parity. Okay, the two conditional probability just equal to each other, and there's no more shaded area. And what's the second rule? Second rule means the accuracy. Okay, so if I use half, that's the misclassification rate, like this shaded area. If I adjust, okay, to this delta, then actually this error will be larger, okay, because there's a misclassification rate. And this error is even larger because I want to have a strict disparity. So you take a higher price in terms of like classification. Okay, you make more mistake. So that's the one. And actually you can tell that there's an intrinsic accuracy and the fairness trade-off. If I want to be more fair, then I will lose some accuracy. That can be precisely mathematically characterized. And we actually use this simulation to verify this trade-off as well. Okay. Okay, then what's the algorithm? So far I only talk about theory, everything theory. The algorithm wise is very simple. And because everything can be mathematically calculated, I can use a way to estimate the t delta hat. And this is, I just use the sample probability to estimate this population probability. And this A hat is the conditional mean, right? Conditional probability that whatever machine learning algorithm you can use to get it. Okay, that's what I meant after processing. Okay, you don't need to change your algorithm to obtain the 8A hat. What you need to do is just to calculate T delta hat. That's how we do the estimation. And the D hat is a plug-in estimator of some like adjustment parameter T. Okay, sorry, I don't write down the full technical details, but I just want to show you, you have an explicit form to estimate the T delta hat. That's the level of adjustment. Yeah.
So, but this theta A is the estimator of the regression.
The probability that y equal to 1 given big A equal to small a. Just yeah.
Okay.
Yeah, right in here. Before the full, just usual way we do the classification. You need to compare this with the 1/2, right? Usually, right? To say, okay, how we classify. So y is 1 or y is 0.
Okay, but then only so you'll be able to use something like logistic regression, but you wouldn't be able to use something like support vector machines.
You can use usually people use the deep neural network to get that pre-op layer, then you can get this problem.
It's basically so you can only use algorithms that you can recover this from.
Yeah, for the estimation of 8, this one I don't need to consider any fairness constraint. I can use a traditional approach. What I need to do, I just adjust this one. I just adjust this. Okay, this one can be guided by any traditional deep neural network. And then you just compare the log with the half, just with this adjusted threshold. That's a contribution. So we tell people how to adjust to make a fair decision. Okay.
And what is the T delta star?
T delta star is I included somewhere here in the appendix. Let me see where it is. Yeah, here it is. It has a need some time to but we have a explicit form to solve it. Yeah. Okay. Sorry, I probably don't. Yeah. The delta is usually given. Yeah, it's not the data dependent. It's given. The disparity level is given. We don't need to ask.
I understand. I mean, the T delta fetch is supposed to be an estimate of T delta.
Plug-in estimator of this definition.
It's not obvious that it's plug-in estimate.
Yeah, there are some mathematical derivation I didn't put here. Yeah, that's just a math formulation, but there are some steps to show why it is a consistent plug-in estimator. Yeah. A good question. Yeah, I skipped that. So we apply that to the real data. It's a very famous law school data. They want to see predict why the student gets admitted. I mean, is that relevant to the race, white versus non-white? And actually, we compare with, of course, we need to compare with the baseline algorithm. Actually, this is our proposed. Actually, you can tell that our accuracy compared to this for like a competing algorithm, our accuracy is not so good. It's not the best, it's close to the best, but our disparity level has been well controlled, okay? For the other approach, you want to get a high accuracy, but your disparity you sacrifice a lot. Okay, we have very precise control. Okay, and actually here is the right curve is our method. Okay, the y-axis is the accuracy. Here is the disparity level. You just look at the left one, you got the same result. Actually, DEO is another type of disparity. I didn't define here. So you just look at the DDP. So you tell that as we relax the fairness constraint, we didn't lose too much in terms of accuracy. Not like this approach, say, okay, I want to have like a fair algorithm, but I have to have a very big loss in terms of accuracy. You see this line is pretty flat. Okay. The reason is that that's a theory is fair. The other approach, I don't have time to go through that, more like engineering. They don't have a theory support, or they adjust the threshold and many things related. Okay. I think that's pretty much all. Okay. I think that's what my lab's working right now, and I'm recruiting. Just moved to UCLA, so I want to take this opportunity to like recruiting student postdoc. I think that's all. Yeah. Yeah.